All right, let's just jump right into this explainer. We're looking at how AI is completely transforming the automotive industry. Now, I know we hear about self-driving cars in the news constantly, but we're going to do something a little different today. We're taking those big, abstract concepts of vehicle autonomy and bringing them all the way down to the asphalt, specifically onto a test track with massive, heavy-duty semi-trucks. So, the roadmap for today. We'll be heading 5 key stops. First, the mobility revolution. Second, the levels of autonomy. Third, how autonomous vehicles see. Fourth, the truck platooning study. And finally, number 5, when sensors fail. But before we get bogged down in the mechanics and the data, I want you to keep one ultimate question in the back of your mind. Will we ever completely let go of the steering wheel? That is the ultimate promise of all this self-driving hype, right? But as we peel back the layers on the actual tech today, you're going to see that hitting that goal is an absolutely massive engineering challenge. Section 1, the mobility revolution. To see exactly where we're headed, we really need to look at the massive shift happening right under our feet. We're basically smack in the middle of a major technological disruption, driven by 4 main trends that all feed into each other. We've got autonomous driving, shared mobility, connectivity, and electrification. And why does this matter to us? Well, the benefits are pretty staggering. We're talking about better safety, simply because AI doesn't get distracted checking a text message. We get way more lean capacity because computers can safely drive inches apart. And by combining connectivity with automation, vehicles can do real-time path planning. That alone can slash a vehicle's fuel and energy consumption by 20% or even more. To put that into perspective, just look at the projections for the year 2030. A huge chunk of new car sales, we're talking up to 45%, are expected to be electric. Meanwhile, about 10% could be built specifically for shared mobility, and up to 15% could be fully autonomous. That is literally millions of cars operating out there without a human lifting a finger. Section 2, the levels of autonomy. So how do we actually get to that 15% market share? We don't just flip a switch from human driver to robot driver. There is a very specific roadmap for this, defined by the Society of Automotive Engineers. It scales from level 0, which is just you doing all the manual driving, all the way to level 5. Right now, a lot of the cars we drive sit at level 1 or 2. Think adaptive cruise control or lane keeping assist, where you still absolutely have to pay attention. Level 3 is conditional. The car drives, but you gotta be ready to jump in. Then there's level 4, high automation. Think of those driverless Waymo taxis that roam around specific mapped-out city limits. But the true holy grail, that's level 5, full automation. Anywhere, anytime, any weather. At level 5, your car won't even have a steering wheel or pedals. Section 3, how autonomous vehicles see. Which brings us to the obvious question. How does the computer actually do the driving in the chaotic physical world? Basically, an autonomous vehicle processes its world in 4 rapid-fire steps. Step 1 is sensing. This is the hardware, radar, LiDAR, and cameras, pulling in raw data about the physical environment. Step 2 is perception. The AI takes that raw data and figures out what it all actually means. It identifies a pedestrian, it maps out the lane lines, it tracks the car ahead. Step 3 is path planning, where the system makes a fast decision on what to do next based on what it just perceived. And finally, step 4 is motion control. This is the computer sending actual physical commands to the throttle, the brakes, and the steering wheel to execute the plan. Now, here is the catch. No single sensor is perfect. Cameras get completely blinded by sun glare, radar can get noisy, and GPS, we all know that drops out the second you drive under a thick canopy of trees. That is exactly why these systems rely on something called sensor fusion. Sensor fusion is essentially the mathematical magic that merges all this imperfect data into one highly accurate picture of the environment. They often use what's called a Kalman filter to do this. You can think of the Kalman filter like a master conductor in an orchestra, blending different, sometimes messy instruments together to make one perfect symphony. Section 4, the truck platooning study. Let's take all this theory out of the digital lab and put it onto actual asphalt, specifically down at the National Center for Asphalt Technology test track in Opelika, Alabama. We really wanted to see how sensor fusion works in heavy physical reality. So we're looking at a fascinating study from Auburn University involving Class 8 semi-trucks. We are talking about 35,000-pound behemoths flying down the highway. What's super interesting here is that the Auburn team wasn't trying to build some billion-dollar Level 5 autonomous truck covered in experimental lasers. Instead, they focused on something called Cooperative Adaptive Cruise Control, or a CACC platoon. Basically, a human drives the lead truck, and the following trucks drive themselves, trailing closely behind. And get this, they do it using a really lean, factory-ready sensor package, just standard dual-beam radar, precision GPS, and vehicle-to-vehicle radios that instantly share braking and acceleration data. The results of using this lean AI package? Absolutely massive. By letting these huge trucks safely tailgate each other autonomously, sometimes just 50 to 100 feet apart, they drastically cut down on aerodynamic drag. Catching that slipstream creates incredible fuel savings of about 10 to 12%. And in the commercial freight world, where fuel is literally one of your biggest operating costs, saving 12% is a total game changer. Section 5. When sensors fail. And this is really the crux of our explainer today. What happens to that amazing 12% efficiency when things inevitably go wrong out on the road? To find out, the researchers intentionally sabotaged the trucks to stress test the AI. My favorite test? They literally mounted the radar unit completely backward on one of the 35,000-pound following trucks. Because it was backwards, the radar completely lost track of the lead truck every single time the convoy went around a curve on the track. So when that radar dropped out on a curve, the following truck's AI suddenly panicked. It had no accurate idea how far away the lead vehicle was, so to be safe, it slammed on the brakes. But then, coming out of the curve, the sensors would lock back on, and the AI would realize it had fallen way too far behind. So it aggressively smashed the throttle to catch up. This constant, jerky cycle of aggressive braking and over-accelerating absolutely killed the truck's momentum. It wasted so much energy that it actually caused a 5.68% increase in fuel consumption. A purely digital glitch caused a very real, very expensive physical penalty. But they didn't stop with the radar. They also tested what happens when the GPS gets degraded, like driving on an overcast day under thick trees, and they even parked a transmitter next to the track to actively jam the radio communications between the trucks. But get this, the results were completely different. While that faulty radar caused a massive near 6% fuel penalty, the degraded GPS only caused a tiny 0.25% bump, and the radio jamming, it had a practically negligible impact on fuel. So why the huge difference? Why did the truck power right through the GPS and radio failures, but totally lose its mind when the radar failed? Well, it all comes back to sensor fusion. Our good friend the Kalman filter realized the GPS and radio signals were acting up and getting noisy, so it simply rejected them. It leaned heavily on the one healthy sensor it had left, the radar, to keep the truck driving smoothly. Since radar is the primary tool for judging immediate distance anyway, as long as it worked, the truck never panicked, and it didn't waste any fuel. There's a quote from the Auburn study that just hits the nail on the head. It says, "The mechanism of disturbance remains the same in all cases. Sensor degradation, leading to poor dynamic performance, leading to increased fuel consumption." That basically sums up the entire challenge of autonomous vehicles. If the AI's perception of reality breaks down, if it can't clearly see the world, the physical efficiency and obviously the safety of that vehicle takes an instant nosedive. Which leaves us with a pretty fascinating final thought to chew on. If reaching true Level 5 autonomy entirely depends on flawless sensor fusion, can we ever really trust a machine to interpret our incredibly chaotic world flawlessly? Or will the sheer unpredictability of reality mean we always need a human touch? Bottom line, if we can't completely trust the sensors, we definitely can't trust the drive. Thanks for tuning into this explainer with me, and definitely keep your eyes peeled as these incredible technologies keep evolving out there on the roads.